Alright guys, let's go ahead and take a look at some integral review. I think we're starting off with number 11 this week. Here we go. Alright. Once again, this video is intended to be a helpful thing for you, not just me doing it for you. So I would encourage you guys to definitely try as many of these things as you can and just fast forward to the problems that you actually need help with. So this is an exponential function. It is a U-substitution problem. You can see that this is going to be the U. A lot of times with exponential functions, the power is the U. Not always, but a lot of the time. In general, how you can tell which one is the U is you look for the thing that you want to call U, and somewhere you should see its derivative hanging out there. In any event, we go through all of our steps here. We have this. So let's go ahead and do our U substitution here. I'm going to put an x right here. E to the U goes here. And I'm replacing dx with du over 2x. Now, these things here are going to cancel out. And now we're left with just u's. But we have more work to do here. This is a definite integral, which means that we have to concern ourselves with these values here as well. Those are x values. So I want to change them into u values. The way you do that is by plugging these numbers into this equation for x. So if I were to plug in 0 for x, I would get 0 squared, which is 0. So that would mean that u is 0 when x is 0. And then you can do the same thing for 1. You're going to plug in 1. 1 squared is 1. And so that means u is also 1. So now here's what I have. I'm going to go ahead and rewrite it a little bit nicer. And that 2 on the bottom I'm going to bring to the front as a fraction. And then from here we go ahead and actually do the integration. So the integral of e to the u is e to the u. Next we're going to plug in the numbers and subtract them, right? So it's e to the u. It's going to be e to the first power minus e to the 0 power. E to the 0 power is 1. And so this is what we're left with. Now, how are they going to write the answer is kind of hard to tell. But let's see, because there's different ways they can choose to write this. Let's see. They went ahead and just left it like this. So there we go. I would go with option B on that one. Okay, for number 12, I'm going to go ahead and do another U sub problem here. Oops. Just a second, I got to scroll down. Too far. Alright. Make some workspace. Okay. For this problem, we're going to do some U substitution once again. I'm going to go ahead and let my U be equal to 2 theta. And then we do the derivative of U with respect to theta. Go ahead and do our U substitution. We also need to change these now, right? So I'm going to go ahead and plug these values in. If I plug in 0, I get 0. And if I plug in pi over 4, I end up with pi over 2. 2 times pi over 4 is pi over 2. So next thing I'm going to do is I'm going to pull that half out to the front. And here is our new expression. All right. The integral of sine is negative cosine. Notice I'm not doing the plus c on these problems. When you do definite integrals, you don't do plus c. Okay, so now we're going to go ahead and plug in our limits there. So we have negative cosine of pi over 2 minus a negative cosine of 0. Alright, so cosine of 0 is 1. Double negatives makes a positive. Cosine of pi over 2 is 0, so the negative doesn't matter anyway. And then we have a half. If you do a half times that sum, you end up with just a half would be your final answer there for number 12. Alright, let's go ahead and move on to number 13. Alright. So a lot of times whenever you have an expression in the bottom, that's going to be your u, especially if the derivative of the denominator is in the numerator. So in this case, that's just a negative 1, and that's okay. Constants don't matter. So in this case, my u is going to be the denominator of 3 minus z. So the derivative of u with respect to z is negative 1, which means that negative du is equal to dz. So doing a little bit of U-substitution. Well, first of all, before I start my U-sub, I just want to remind you guys, it's probably wise to write it like this. It just helps a little bit with the way that we do things. But now that we go ahead and do our U-substitution here, we're going to have 1 over u, and it's going to be negative du. Now I'm going to put that in parentheses because I don't want you guys to think that's 1 over u minus du. It's not. It's 1 over u being multiplied by a negative 1 and then du. We also need to deal with these limits like on the last view. So if I plug in 1 here, I get 2, and if I plug in 2, I get 1. So to simplify this a little bit, we have the following. Put the negative out in the front. And it's kind of weird. Usually the bigger number's on the top of the integral, but in this case the smaller one is, and that's okay. That's not going to change anything that we do, but it just looks weird. So now we're going to integrate. The integral of 1 over u du is ln of the absolute value of u. Next, we're going to plug in our limits here. Subtract them. Ln of 1 is 0. And then, so we can just ignore that basically and then distribute that negative, and you're going to end up with a positive ln of 2 as our final answer there, which I'm hoping is option E, because I don't see that there. Let's see. There it is, option E. All right, so number 14. This is an interesting problem. I've seen a few of these before. Basically, it's U-substitution, and they're telling you what the U is going to be. So, in other words, they don't want us to have X anymore. They want us to replace X with this. So if I'm going to be replacing X with that, then I also am going to need to replace the dx and also this with things that involve theta. Okay, so it's a weird question, but it's really just kind of like some weird convoluted way of doing U substitution. So here's my U. My U is going to be this. And what we're going to do is we're going to find the derivative of this with respect to theta. The derivative of sine is cosine, as you know. And then I'm going to multiply both sides by d theta there, because I want to solve for dx. I want to get dx by itself. Why do I want to get dx by itself? Because I want to replace dx with something different, right? So I'm going to replace all the x's with 2 sine theta, and I'm going to replace dx with 2 cosine theta d theta. Okay? So if I do that, this is what it's going to end up looking like. 4 minus x squared is going to become 4 sine squared theta. Because if you square this, the 2, you get 4. And if you square sine, of course, you get sine squared. So there's that. And then on the bottom, we're going to replace the x with 2 sine theta as well. The next thing we're going to do is we're going to replace the dx here with 2 cosine theta d theta. All right, so there's that. Another thing that we're going to have to do is we're going to have to change the limits of integration. These are x values, but we want theta values. So once again, we're going to plug those numbers in for the x so we can solve for theta. So if I take this 2 and, or let's start with the 1 actually. If I plug 1 in for x, divide both sides by 2. So when does sine of theta equal a half? In other words, when is the y value on the unit circle a half? Well, let's see. Here's my unit circle. Sine is a half here, and it's also a half here. And so that's going to end up being at pi over 6 on this side, and on the other side that would be 5 pi over 6, but I have a feeling they're only going to use this one, so let's go ahead and come on back here, and I'm going to say it's pi over 6 on the top there. And then we're going to do the same thing. We're going to plug, this time we're going to plug in the 2, the top number here. So if I put 2 here, that's x is equal to 2 sine theta. Divide both sides. And when is sine theta equal to 1? Sine theta equals 1 whenever it's at the very top of the unit circle, which is pi over 2. So that's going to be pi over 2. I just realized, by the way, I goofed up. The pi over 2 should be on the top, because that's what I got when I plugged in 2. And the pi over 6 should be on the bottom, because that's what I got when I plugged in 1. So right away, we know that this is not the answer, and this is not the answer, this is not the answer, because of my limits. It should be pi over 2 on top and pi over 6 on the bottom. Now, you guys might be looking at this mess here and wondering, what the heck, how did they get here? Well, at this point, we have some other considerations that we're going to need to look into here. And that's some trig identities that you may or may not remember from last year. I don't know how big of a deal this is on your AP test. It can't hurt. I know that this test booklet that I give has a lot of these. It's not a terrible thing to review. It's kind of a pain in the butt, but let's do it real quick. So first of all, I want you guys to focus on this piece here with me real quick. Okay. Now, first of all, I'm going to factor a 4 out. Why would I do that? Well, because once you factor out that 4, you could square root that separately from this piece here. Okay, the square root of 4 is 2. Now we have this piece right here. Now this is a trig identity. I don't know if you guys remember this one from last year or not. You guys remember that this is equal to 1? And if you were to subtract sine on both sides, you would get this. All right? So that means that 1 minus sine squared x is equal to cosine squared x. So I can replace that with cosine squared x. And the square root of a square cancels out the square, and this is what I'm left with. So all that fun math there kind of can be condensed then into the following expression. So Where did we go? I lost my work. Just a moment. So what I'm going to do then is we just realized I can simplify this whole thing on the top here to be rewritten as 2 cosine theta. So that's the only part of this problem that I'm a little bit irritated with. I know that most of you guys aren't going to remember that identity. That's pretty hard to remember. But as you guys can see, this 2 is going to come out to the front. I crossed off these 2's, right? This 2 I'm going to bring out to the front, so I'll cross that off. And then cosine and cosine makes cosine squared. So we would have this as our final answer, which you guys can see is option C. So I think the problem with this exercise, and honestly, if I'd known this was coming, I might have just not assigned it. But I'm kind of glad we did. It's good to see those identities. It's possible that they could come up again. But honestly, what I do really like about this problem, though, is this whole thing where we had to do that substitution of a different thing. I think that's actually a pretty cool skill to have. I have seen questions like that. So in spite of the whole trig identity thing, which isn't terrible to review, I really like the U-sub thing that we get to do there. So I think we get to do it again, actually, in another problem. So let's go ahead and take a look at number 15 now. Number 15. It's a U-sub problem. It's a U-sub problem. So on this problem, what do you think the U would be? You have 3 options: sine, cosine, or cosine squared. Which one of those, if you took a derivative, you would see that thing left and would cancel out? And hopefully you guys are recognizing that it would be the cosine. Cosine theta is your U, because when you take the derivative of that, you get negative sine theta, and that negative sine theta is going to cancel out this other sine theta. Okay? So the cosine squared theta becomes U squared. And then we still have our sine theta here. And now we're going to replace, let me solve this a little bit more. And I forgot to get the d theta by itself. I can replace d theta with du over negative sine theta. Now the signs cancel out, but I still have a negative there, which I'll just go ahead and move out to the front. Another thing that we need to do is we need to do something about these. These are theta values, but now we need a u value. So if you plug in pi for cosine, you're going to get negative 1. And if you plug in 0, you're going to get positive 1. So the clean version of this would look like this. And then from there, we just go ahead and evaluate the integral. So the integral of u squared would be u cubed over 3. We have a negative out there, and my limits are negative 1 and 1. We're going to go ahead and plug those in. If I plug in negative 1 and cube it, I get negative 1 again. Minus, plug in positive 1, cube it, you get 1 again, so it's 1/3. So go ahead and distribute this negative, everything becomes positive, and you end up with 2/3 as your final answer there. All right, chugging along some more. Number 16. All right. This one's interesting. It's another U-sub problem. What do you think the U is this time? Well, if I take the derivative of ln of x, I end up with 1 over x. And that 1 over x will probably end up canceling out this bottom x, which is what I want to have happen. So I'm going to multiply both sides by dx first, and then I'm going to multiply both sides by x after that. And so we end up with x du equals dx. Doing our u-sub, we end up with u over x, x du. And the x's go away. We also need to deal with our limits here. So if I plug in 1, I get 0, and if I plug in e, I get 1. So the simplified version of this U-substitution would look like this then. From there, we're going to go ahead and integrate. So if you add 1 to the power, you get square and divide by that number. My limits are 0 and 1. Plug in the 1, plug in the 0, subtract them. You end up with a half as your final answer. All right. 17. This is a BC problem, so we'll be skipping number 17. It may look simple, but it's actually different. It requires a strategy known as integration by parts. All right. As for number 18, we have a fraction, and a lot of times when you have fractions, not always, like the last problem was an exception, but most of the time the bottom is what your u is going to be. So I'm going to say that my u is equal to 1 plus 2 sine theta. And so if I take the derivative of that with respect to theta, the 1 goes away when you take a derivative of it. And then we have 2 cosine theta. Derivative of sine is cosine, and the constant multiple just stays the way it is. Get the d theta by itself. All right. So now I've got cosine theta on the top, u on the bottom, and then I'm going to replace my d theta with du over 2 cosine theta. Oops. And then my cosines go away, and I'm going to pull the 2 out to the front. And we also need to do something about our limits here. So I'm going to plug in 0. Sine of 0 is 0. So 1 plus 2 times 0 is going to be 1. And I'm also going to plug in pi over 6. Now, sine of pi over 6 is a half. So 1 plus 2 times a half is going to be coming out to be 2 in the end. So now we have the clean version. The integral of 1 over u is ln of the absolute value of u. And our limits are 1 to 2. Let's plug in our numbers there. Ln of 1 is 0. So here's what I'm left with. Sometimes with logs, the way that you have your answer written changes. Let's see, because you can do log properties to write your answer in a different way. Let's see, do we have that answer up there anywhere? We kind of low-key do, but it's hard to see. I'll show you. And this is going to probably be frustrating to you guys, but it's weird. You would probably be tempted to pick this one, but that's wrong. Let me show you what the answer is. So this is our answer, right, that we got. Now here's the deal. Log properties tell me that this can be rewritten as an exponent like this. And a half power can be rewritten as a square root. So my answer is E. So yeah, I don't know how big of a deal they make of rewriting logarithmic expressions on the AP exam, but can't hurt to review it once again, so we'll look at it. All right, let's go ahead and take a look at number 19. All right, once again, when you have a fraction, a lot of times the u is going to be the bottom part of your fraction. And in this case, that still applies. So now I'm not going to use U-substitution. I'm going to do W-U-substitution because they're already using the variable u there. That would be confusing. So we're going to say that W is equal to u squared minus 1. The derivative of W with respect to u is going to be 2u. And then dw over 2u is equal to du. It's time for our u sub. So the u on the top is going to stay. The bottom is going to be replaced with w. And du is going to be replaced with dw over 2u. And the u's cancel, and I'll be moving the 2 out to the front. The next thing we need to do is we need to deal with our limits of integration here. You're going to plug them in. So if you plug in 2 squared is 4, take away 1 is 3. And we're also going to plug in a square root. If you plug in a square root, you get 2. 2 take away 1 is 1. So the clean version of this thing then would look like the following. There you go. And once again, when you integrate this, that's an ln, right? So now we're going to have 1/2 ln of the absolute value of w from 1 to 3. Plug them in, and go to town. Once again, ln of 1 is 0, so we have 1/2 ln of 3. It's our final answer. Do they have that? They don't have that answer, but they're doing the same thing that we learned in the last problem, which is where this becomes a power, log property, right? And then that means square root. So the answer is A. All right. Number 20. Same problem almost. My w is going to be the bottom of the fraction like usual. The root of that is going to be 2u. dw over 2u gives me du. U-substitution time. U stays on top. I don't like it when they put the du on top. I'm going to move it to the side. And we're going to replace that du with dw over 2u. And we're going to replace the bottom inside of parentheses there with a w, and it's being squared now. That's really the only difference. Plugging in your limit. Square root of 2 squared is 2, take away 1 is 1. Plug in this limit, 2 squared is 4, take away 1 is 3. So if we put this half in the front and cross off these u's, here's what our problem will look like in a simpler format. Alright, so what's different about this problem is that now instead of just 1 over w, it's 1 over w squared. And that means we're going to handle the problem a little bit differently. It's not an ln problem anymore whenever it's like that. When it's not just a power of 1, but some other power, what we're going to do is we're going to move it up to the top as a negative exponent. And what we're going to do is the power rule. That's where you add a number to the power, right? To integrate it, I mean. So if I were to add 1 to a negative 2, I would get negative 1. And then you divide by that number. Now this is not really a very workable thing either, so I'm going to rewrite that as well. W to the negative 1, what that means is the w is going to go on the bottom of the fraction, and the negative 1 is going to end up just making the fraction itself be negative. So there's that. And then from there, we're good to start evaluating this thing and figuring out the final answer. So let me make some room here. Okay. So if I plug in the 3, I get that, minus, then we'll plug in the 1. So these are going to become plus, and in order to put those together, we're going to need to get a common denominator here. So what I'm going to do is I'm going to multiply the top and bottom of this by 3. 3 and negative 1 combine together to make 2. And if you multiply, well, actually, these are just going to cancel out, so I'll be left with a third, basically, as my final answer. Okay. All right, moving along. 21. All right. All right. So this is kind of an odd problem. What do you think your u is going to be? Well, once again, usually it's the bottom, but it's not going to be the whole bottom, right? It's the bottom is being squared, so it's sine squared 2x. So my u is going to be this. Okay. So a good way to think about this would be like as though you had sine of 2x and it was being squared. That's another way of writing this. And this is going to be my u, just so you guys know. It looks weird, but that's how they have to write trig functions. So, du dx, it's a chain rule here. The derivative of sine is cosine. Don't change the inside. But we are going to multiply it by the derivative of the inside, so it's a 2. Okay? And we want to get the dx by itself like usual. And then we're ready for some U-sub. All right, so integral cosine 2x over u squared, and we replace the dx with du over 2 cosine 2x. Those cancel, and we put the 2 in the front as a half there, and we end up with pretty much the same integral problem we had in the last one. The limits are different though. I haven't done the limits yet. I'll get them. This time for my limits, we're going to be plugging in pi over 4. So if I plug in pi over 4 here, if you multiply pi over 4 by 2, that's what you would have to do first. That's going to end up being pi over 2. And sine of pi over 2 is 1. So by plugging in pi over 4, I end up with 1. Repeat that process with the other one. So now I'm going to plug in pi over 12. So if I plug in pi over 12, that's going to result in sine of pi over 6. Sine of pi over 6 is a half. And there you go. All right. So once again, since this is a square and not a 1, we're going to handle this with a reverse power rule. So it's going to end up being u to the negative 2 du. Now if I actually integrate this, we're going to end up with u to the negative 1 over negative 1. All right. So once again, we want to rewrite this. The u is going to go to the bottom, and the negative 1 is going to make the whole thing become negative. So we would have this. Same integral as last time, just different limits. And we're ready to roll. So I'm going to plug in 1 there. Get negative 1 over 1 if you do that. Minus, plug in your half. That's interesting. 1 over a half. What the heck is that, right? We talked about those a little bit earlier this year. First of all, double negatives is positive. Second of all, the way that I taught you guys to deal with these complex fractions is just to multiply this fraction by 2 so that that cancels. But whatever you do to the bottom of that fraction, you got to do the top also. So this ends up basically just becoming 2. So we end up with 1/2 times negative 1 plus 2. Now this -1 and 2 just makes 1, so 1 times a half is just going to end up being half as your final answer. So there's that one. All right. We're really hitting up the U-sub today. All right. Actually, this problem's interesting. It's I don't think this is actually going to be a U-sub problem. I wonder if you could solve it as a U-sub. But I'm going to approach it from a slightly different angle here. Now, when you have a fraction, one of our rules is that a lot of times your U is going to be the bottom, right? But I'm kind of giving you a heads up here. That's not what's going to happen on this one. Here's another thing you want to watch out for. Anytime you have a binomial or a trinomial or more than one term in the top, very often that's a problem where you want to split it up. What do I mean by split it up? I mean split that one fraction up into two separate fractions, like that. Okay? Now check it out. What is that? Anything divided by itself is 1. We can also simplify this. That negative exponent is going to cause it to go to the top, and you just end up with e to the x over 1, which you can just write as e to the x. And you end up with a much simpler looking integral that way. So for this one, we're going to integrate the 1 and the e to the x. So the integral of 1 is just going to be x. And the integral of e to the x is e to the x. So now we're going to go ahead and we're going to plug in 1. So if I plug in 1, you got to put it in both spots there. And then we're going to plug in 0, both spots. All right, so I have 1 plus e here, right? Minus, this is 1. 0 is just 0, and e to the 0 is 1. So we have 1 take away 1, and I'm left with e as my final answer there. So when you have a fraction, a lot of times your bottom is your u, but if your numerator has more than one term, a lot of times, and this is not always, but most of the time, that's just going to end up being a problem where you split it up into two separate fractions and go ahead and follow your lead after that. But let's go ahead and continue here. Now in this case, it's different. Okay? So remember how I said when your numerator has more than one term, you split it up? Well, that's not what we have this time. This time, it's my denominator that has more than one term. In that case, we're going to backpedal and we're going to do the other rule that we had earlier, which was we're going to let the bottom be our u. So the derivative of u with respect to x is going to be e to the x. The derivative of e to the x is just e to the x, and the derivative of 1 is 0. So we're good there. Go ahead and get that d to the x by itself, and let's do our U-substitution. Right? Those cancel. We also need to do our limits here. So if I were to plug in 1, I'm going to end up with e plus 1. If you plug in 0, you end up with 1 plus 1, which is 2. So the cleaner version of this then would be e plus 1, 2, 1 over u du. Now in this case, we have a 1 over u and it's to the first power. That's an ln problem. Okay. So we plug in the first one there, we're going to end up with ln of e plus 1 minus, plug in the 2, ln of 2. Now some of you guys might be wondering, why am I getting rid of the absolute value bars? So it's because these are positive numbers anyway. E is positive and so is 1, so there's no point in having absolute value bars there. Now I don't see that answer there, but do you guys? It's there and yet it isn't. See if you can think of what log rule you can use, which one would work there. All right, so here's the log rule. When you have two logs that are being subtracted, you could write those as one logarithm where this one's argument is being divided by this one's argument. So the answer would be E. They're doing more with the log rules there. All right. Let's see. Bring this down a little bit. Okay. Oh boy, another one of these. So once again, if I were you, I would encourage you guys to go back to number, I think it was 18? No. There it is, number 14. I would go back to number 14, review how to do it, and I would highly encourage you guys to try this next one on your own if you can. Now, if you can't, you need to watch, that's fine. But, you know, you want to get to a place where you can start doing some of these things on your own, because these are a little weird, a little different. So in this case, it says, if we let x equal tangent theta, then how can we rewrite that integral, basically? So what that means is they want us to replace the x with tangent of theta. But if you do that, you're going to have to replace this with a d theta, and you're going to have to replace these with thetas also. Okay? And you can narrow down your options a lot by just getting these. And we saw that in the last problem. But anyway, let's go ahead and continue here. So I'm going to say that x is equal to tangent of theta. We're going to find dx d theta. Derivative tangent, it's been a while, but it's secant squared. Now here's another thing that's different. Usually when we do U-substitution, we switch these two things, right? But this is going to be a little bit different, because remember, I want to get rid of the dx, right? So I want to get dx by itself. So I'm going to multiply both sides by d theta. That way I can replace dx with this instead. Okay? So here's where my integral is looking like so far. We have square root of 1 plus, instead of x, I'm going to have tangent squared theta. And I'm going to be replacing dx with secant squared theta d theta. We also need to replace these things. So if I plug in square root of 3, oh my goodness, do you guys know your tangent values? I don't know. Let's see. That's interesting. So tangent is equal to the square root of 3 up here. Now I had my students memorize their tangent circles last year. I'm not sure if you guys did or not. But that's where tangent is equal to the square root of 3, and that's at an angle of pi over 3. Okay, so when theta equals, I'm sorry, when I showed plugging that in incorrectly, actually. Back up a little bit. We're plugging it in for x. So when you put radical 3 over there, theta is equal to pi over 3. Okay. We're also going to plug in 1 now for x. When does tangent equal 1? Tangent equals 1 at the middle, which is pi over 4. So right away with those two things, we're good, and we can kind of narrow down our options. I know it's either A or D. Oh, actually C snuck its way in there too, darn it. All right. At this point, you got to know your trig identities once again. What is 1 plus tangent squared theta equal to? So I don't really remember that one either, so what I do is I just try to figure it out, but some people have memorized them, and if you haven't memorized, just use it. But you guys know, hopefully, this at least, that tangent is equal to sine over cosine, right? So remember that one I showed you back on number 14? If I divide everything by cosine squared, I end up with sine over cosine, don't I? And it's being squared, so that's tangent squared, right? C over C is 1, and 1 over cosine is secant. So what that means is that 1 plus tangent squared is equal to secant squared. So in our problem, we're looking at this, right? But now we know that 1 plus tangent squared is equal to secant squared. And a square root cancels out a square, so it's just secant. Okay? So this whole thing here just can be replaced with a secant. And secant times secant squared is secant cubed. And so we have our answer right there at C. All right, moving along, moving along. 25. Ooh, boy, another one. All right. Craziness. All right. So, if the substitution u equals the square root of x plus 1 is used, how can we rewrite that expression over there? All right, well, let's do it. So, the derivative of u with respect to x, hopefully you guys know your shortcut for finding derivatives of square roots. Usually need to multiply it by the derivative of the inside, but the derivative of the inside here is 1, so that's good. And remember, I want to get everything with a u now. So I want to get dx by itself. So I'm going to multiply both sides by dx first, and then I'm going to multiply both sides by that. And so if you do that, you end up with the following expression. And now we're ready for our U-substitution. So we have, and remember, I don't like those up there. I always put them on the side. Put a 1 there instead. So now I've got 1 over x u, right? And then I'm going to replace the dx with 2 square root x plus 1 du. Now, this one is interesting because nothing cancels. Usually at this point, something cancels. So we are going to have to do some weird things here. Before we begin, though, we probably won't eliminate many options by finding the limits. It's either going to be 1 and 2 or 0 and 3. It's probably not 0 and 3 because that's what it was. We'll go ahead and do it. What the heck? Let's go ahead and do it. So take your 3, plug it in. You get 3 plus 1 is 4. Square root of 4 is 2, so this becomes 2. Take your 0, plug it in. 0 plus 1 is 1. Square root of 1 is 1. So there we go. So we know it's not any of these ones with the 0 and 3 on them. All right. But now what? What the heck are we going to do now? There's an x in there on the bottom, which shouldn't be there. And there's also a square root of x plus 1. Now here's a weird thing. That is our u. So we actually get to go back and do a whole other u substitution here. And I'm going to erase that. I'm going to replace it with a u. Which means these u's cancel. Now I don't really want my u's to cancel, but it's okay if they do. But the problem is we've got this now. It's much simpler looking. I guess I'll put the 2 in the front. We have 1 over x du. Now the problem is I have an x. I don't want x's, I want u's. So we did talk about these problems briefly way back in like September. So you guys probably don't remember, but hey, that's what review's all about. So what do we do whenever there's still an x in there after we do the u substitution? Well, what we do is we revisit this little equation right here. What I'm going to do is I'm going to get x by itself. So I'm going to square both sides and then subtract 1. Oops. So now I see that x equals u squared minus 1.
This is a test page. Testing.
And there you have it. So replacing the x with u squared minus 1, we get that. And we have our answer. So which one of those does it fit? This one's close, but it's no good because there's no 2 in the front. This one has a 2 in the front, but it has an extra u on the bottom, so that's no good. We already said it wasn't these. So this is our answer. Now here's what they did. They decided to leave the 2 inside and leave the du on top. It's the same thing though. So the answer is B. So the main thing to walk away from with this problem is to realize that when you still have an x left over after you do your U-substitution, you go back to the original U equation and solve for x to replace it in that way. Okay. Continuing on. All right. The table shows some values of continuous function f and its first derivative. Evaluate this. Now, this is a weird question. It's definitely a major gear switcher. We're not doing integrals by hand. So here's what you guys need to remember. Integrals are the opposites of derivatives, right? So if you have a function and you take the derivative of that function, you get the derivative, right? Or if you have the derivative, and working backwards, if you integrate it, you get the original function. So the thing I want you guys to pay attention to is that when you integrate a derivative, you get the original function. So that's how we're going to have to think about this problem here. So if I'm integrating f prime, that's going to become f, right? Now here's the first fundamental theorem of calculus. The first fundamental theorem of calculus tells us that if you're doing a definite integral of a derivative, when you integrate this, it becomes f, and you're going to plug in the upper limit and the lower limit and subtract them, right? So that's the idea. So in this case, my limits are 0 and 8, but they're backwards, so you got to pay attention to that. So if I integrate this, then basically the integral of f prime gives me f, and when you plug in your upper limit, that's what comes first, your lower limit comes second, and now we just use the table. So f of 0 is 11, and f of 8 is 7, for a final answer of 4. All right, moving along. So I don't know why they use this notation. I haven't really ever seen this notation in any other book I've used, but what this means here is they want us to do a midpoint sum. So we're going to make rectangles out of the midpoints there. And what the 3 means is they want 3 subintervals. So let's begin. The first thing we're going to do is we're going to take our last x value and we're going to subtract from it our first x value from 6 to 0, right? And we're going to divide that up into 3 equal chunks, which equals 2. So we're going by 2's. So here's my first interval. I'm going to color code these just so it's a little bit easier to see. Here's my next interval, and then here's my last interval. Now when you're doing midpoint sums, what you do is you use the middle. So for this black line, the middle's here, right? So I'm going to go up and find where that would be on my curve. That's here. And that's my first rectangle. Repeat that for the brown one. Middle's here, so go all the way up. Probably somewhere like right about there. And then for the red one, middle's here, so go up to about where that midpoint would be on the curve. Draw your rectangle, and there you have it. So there's our 3 rectangles. Now, each of those rectangles have a base of 2, right? So that's pretty easy to see. The problem is the heights. I don't think I would be comfortable with saying, oh, well, you could see this one's 4. It might be, I don't know. But what I would feel more comfortable with is I'd say we should probably just use the equation. Okay, so what is the height of this point? Well, we know the x value at that point. The x value is 1. So if I plug in 1, I'm going to get 6 minus 1, which actually is 5. So the height of this first black rectangle is 5. So 5 times 2 gives me an area of 10. Let's do the next one. What's the height of the brown rectangle? Well, at x equals 3, if we go ahead and plug 3 into our little equation over here, six times 3 minus 3 squared is 18 minus 9, which is 9. So my height is 9. So I have 2 times 9 is 18 is the area of the brown rectangle. And then finally for the red rectangle, my x value of the midpoint, the height of that rectangle in other words, is going to be at x equals 5. So if you plug in 5, you get 30 take away 25, which is 5. And remember, this one was 5 also, so the way I drew my picture is a little goofy, but that's why I say I really didn't want to look at just the axis and guess. So 30 take away 25 is 5. 5 times 2 is 10. So the three areas I have are 10, 10, and 18, which is going to leave me with, what, 38? Final answer? So there you go. There's your midpoint sum. So this means find a midpoint sum using 3 subintervals. All right, next one. All right, the graph of a continuous function f passes through those 4 points there. Using trapezoids, we can estimate what? All right, so let's begin. You can do this as a table or as a graph. It's kind of your call. I'm going to go ahead and do graphing myself. What do we have here? We've got 4, 2. We have 6, 6. The only problem with graphing is that you probably should label your points so that you make sure you get your heights right when you do your calculations. 7, 5. And 10, 8. Okay, and we're going to be using trapezoids. So trapezoid, you just take these, you drop them straight down, connect the endpoints, and you're just going to find basically the area of each trapezoid that you're working with. So the area of a trapezoid is the height divided by 2 multiplied by the sum of the bases. And you got to remember, it's a little bit weird, but the height is actually this length, and the base is actually, the bases are these ones. So to calculate the area of that first trapezoid, my height is 2. My bases are, this one is 2, and this base is 6. Oops, not that. So that's going to be 8, and this is 1, so that answer comes out to be 8. Next trapezoid, the height is 1. The bases are 6 and 5, which comes out to be 11 halves. Next one, we have a base of 3, a height of 3, and bases of 5 and 8, which is 13. 13 times 3 is 39, so we end up with 39 over 2. So I'm going to add the ones that are both fractions first. 39 and 11, if you add those together, you end up with 50 over 2, which is 25. And then if you add 8 to 25, you end up with your final answer of 33. So D is our answer there. All right, moving along. Number 29. All right, so once again, they're using that weird notation. L2 means we want to do a left-handed sum with 2 subintervals, and R2 means we want to do a right-handed sum with 2 subintervals. So we're going to go ahead and do both. Now let's kind of like look at the problem though and understand it a little bit. The area of the shaded region of the figure is equal to exactly ln of 3, and if we approximate ln of 3 using a left-handed sum and a right-handed sum of 2 subintervals, which inequality follows? Basically, you end up with the actual area. Now the actual area is the integral. They already told us the actual area is ln of 3, right? But they're writing it as an integral, as you can see. So it's an integral from 1 to 3 of the function 1 over x dx. So this represents the actual area, which we already know is ln of 3. And since we're doing a left-handed sum, that would be an overestimate. And we're also going to do a right-handed sum, which would be a underestimate. And so we have an inequality where the left side is going to represent the underestimate, the right side is going to represent the overestimate, and the actual area is going to go right in the middle. So that's kind of the setup that they're going for there. So basically we just need to find out what the right-hand sum is, what the left-hand sum is, and then we just need to pick the right choice. Now, since we're going from 1 to 3, right, that's the area we're looking at from 1 to 3, we know it's not this because our integral, their integral is only going from 1 to 2. We're not going from 0 to 2 either. We're not going to do 2 to 3 either. So it's either E or B. I guess technically they could ask us about these ones though. So we'll see. We'll see. Because I mean, we don't need to do both, but we'll see. I think it's going to be B or E. Since they said we have to do 2 subintervals, I think you have to do the whole thing there, 1 to 3. All right, so if I'm doing a left-handed sum, these would be my rectangles. Now my bases are 1. Oops, goofed up. Sorry, just a minute. These are my rectangles if I'm doing a left-handed sum. So my bases are 1. What's the height though? Well, the height of this rectangle is the y value when x equals 1. So if I plug in 1, I'm going to get 1. So that point right there where it touches is at 1, 1. So the height is 1. So 1 times 1 is 1. For this one, the height of this rectangle is the y value of that point right there with the left-hand edge touches the curve. So that has an x value of 2. So if you want to find the y value, plug in 2 and you get a half. So the height of that rectangle is a half. So we have 1 times a half, which is a half. So if we add those together, common denominator, 3 halves. So the overestimate is 3 halves, and that's this one. So the actual area is less than the overestimate area, which is 3 halves. Now just for the heck of it, I'll do the other one as well, but I'm pretty sure E is going to come out to be the answer. So now I need to make sure that the underestimate is 5/6. Now if I was actually taking the AP test, I'd probably just stop there and move on to the next question, because at this point you're just kind of like double checking your work, and that takes a lot of time. There's a time and a place for that, but I don't know if you always want to use your time in that way, because they make you move pretty quick on these problems. Anyway, so now for the underestimate, we're going to do the right-handed sum. So for a right-handed sum, it looks like this. Now for this rectangle, the height is determined by the y value of that right-hand corner point, which is at x equals 2, which we already know is a half. So for this first rectangle, the base is 1 and the height is a half, so the area is a half. For this next rectangle, its height is determined by this right-handed point, which is at 3. And if you plug in 3 for x here, you're going to get 1/3. So the height of this rectangle is 1/3, and the base is 1, so 1 times 1/3 is 1/3. And then we need to add 1/2 plus 1/3, getting a common denominator, so we can actually add them together. Gives me 3/6 plus 2/6, which is 5/6. And yes, so the underestimate is 5/6. So The underestimate's 5/6, the overestimate's 3/2. The actual area should be somewhere in between. Our answer there will be E. Cool question. I like it. Let's go ahead and move on here. Get to do more Riemann sums. Yay! I like this question too. This one's really cool. Kind of really tests to see if you truly understand what's going on here and all this stuff, rather than just following steps, right? So let's go ahead and take a look at it. So suppose I have an integral here, which I'm going to call A. Now that represents the area under the curve for the cosine function dx. Now we're going to do a left-handed sum, a right-handed sum, and a trapezoid sum. And they're all going to have the same number of subintervals. But the only thing that matters is that they're the same. It doesn't matter how many there are. Okay? They want to know which of these statements is true. So like for instance, this first one here, A, what that means is that the left-handed sum is less than the actual area, which is less than the trapezoid sum, which is less than the right-handed sum. So how the heck are you going to know that? Well, first of all, it's kind of important you understand what the graph of cosine looks like. Okay? So cosine starts at 1 and then it goes down like that, right? Now 1, it hits here at pi over 2, which is a little bit more than 1. So 1 is here. So we're really only looking at maybe this much of our graph here. So all we know is that basically we don't know how far it's going. We know it's going to 1. The y value don't really care about, but there it is. So here's what matters about this. It's decreasing. And that matters because that affects whether a left-handed sum is an overestimate or an underestimate. So let's ponder here. What's the left-handed sum? Well, left-handed sum is going to be an overestimate, right? Even if you wanted to break this up into 100 pieces, you're still going to have pieces hanging over the edge. So the left-handed sum is an overestimate. The right-handed sum is an underestimate, right? So if we wanted to go backwards and do a right-handed sum, it would look like this. Kind of drew that funky, but there it is. So right-handed sum is small, left-handed sum is big. So we know this is wrong. L can't be the smallest. L has to be the biggest. So it's one of these two. Okay? R has to be the smallest. This is still a possibility, but right now C and D are looking pretty good because L has to be the biggest and R has to be the smallest because L is an overestimate and R is an underestimate. Okay, so now what? Trapezoid sums. Well, if you did a trapezoid, I'll just do one. They say do 100, but it doesn't matter. What do you notice about the trapezoid? The trapezoid is going to be an underestimate also. So the trapezoid is less than the actual area. So left-handed sum is the biggest, right-handed sum is the smallest, trapezoid needs to be less than area. There's your answer. So that's kind of a cool question. I like that one. All right. Makes you think. The only thing I didn't like about it is that you guys probably wouldn't have even known how to start because of the fact that you don't realize maybe that you have to think of this as a picture. And even if you did realize that, do you know what cosine looks like? That's another issue. All right. And I think that's all I assigned to you guys for this week. So we're stopping at 30, and I'll let you guys go from there. So I hope that was helpful.